All right. Yeah, there we go. I'm currently the co-chair of the LibreBMC working group, which is a working group under the Open Power Foundation. And I will just describe that a little bit. And then the DC-SCM, that is a working group under the OCP, the Open Compute Platform. And these two things are synergistic. I'm going to talk about some of the work that's been going on there. First of all, LibreBMC. So Libre is French for free, but it means free as in open and uninhibited, not free as in free beer. So keep that in mind. So I'm a huge fan of free beer. So. Now to do this. One too many, right? Okay. Now here's an overview of the project. I can't get too far away from Mike. The goal of LibreBMC was to take an AC922. I was talking about these. This is the sort of the initial goal. Take an AC922 and replace the existing BMC card in there. It's a baseboard management controller card, and it does things like lights out management, it powers the system on and off. If you don't know what a BMC is, it collects errors and sends it back to the system management console. There's a problem today with BMC. So what a lot of data center providers are finding is that the BMC is an attack vector from a security perspective. There are backdoors in some of these chips. Normally, like the chip right here would be like maybe an A-Speed AST2500. That's what's on the AC922. And there are ways you can get in there, and they don't trust that hardware. So what they're thinking is that you could take a card, a baseboard management controller card, pull it out, put your own card in there, and that card would then have an open solution on it. So what we're trying to do is prove that you could do that. There's a lot of skepticism that says you can't run an FPGA. It's not powerful enough to actually boot a modern computer server. Well, the AC922 is a modern server, right? It's the compute node in the Summit computer system, which is running at Oak Ridge, is still number 4 on the top 500 supercomputers. That's a real honest to goodness server. So we have so the goal of this project is to prove you can take an FPGA with everything open on it and be able to boot that server. So you take we have an Open Power ISA. We're using the Open Power Core microwatt. That's to replace the ARM core that would have been on the ASIC itself. There's open peripherals with LiteX, so all of your gateway peripherals that are around your core, your Ethernet, your I2C, UART, all of that is also open. And then it runs the OpenBMC firmware stack. And OpenBMC was already running on the AC922. And one reason we picked the AC922, it is a completely open platform. Other than the hardware, right? So that from OpenBMC on up the stack, the firmware is completely open. It's one of the few servers that's like that. So do that, and then use these emerging DC-SCM and DC-SCI standards, which I'll talk about what that means a little bit later on. But this is a DC-SCM form factor card right here with a DC-SCI connector. So fit into that standard so that somebody could grab one of these cards with an FPGA on it, plug it into their own data center compute node, and then it would run a completely open and secure solution. Yeah, so the whole push for security. So if you had a problem, say, like Spectre meltdown, we all know about that security problem, right? On the actual was on the compute processors, not the BMCs. But when that hit, and everybody in the industry had to patch around that using software patches, that consumed 10% of the total processing power, like at Google. So they lost right there 10% of the processing power. If that would have been an FPGA, so if you had a problem like that on a BMC and you are able to fix that, you can fix it by just rolling out a new FPGA image out to the field, and it solves that problem, and you don't have to work around it with a software patch. Here's a link to the project, and that'll be on the last page as well. And then there's a demo I'm going to show that shows the solution booting. But first, I'm going to give you a little background on where we were, how we got to this point, and what this project has been doing to get to the point where we could actually meet the milestone of booting an AC922 using that solution. This is a picture I drew back when we were first at my old role when we were architecting the AC922 to just help me and everybody else understand what are all the components that go into a supercomputer. So this is the here's the BMC. So that's really the BMC hardware and firmware components. And it talks then up to the processor. So this was a 2-socket processor solution. And then it had 3 GPUs. This is the Summit at Oak Ridge, and the Sierra version had only had 2 GPUs, but it talks over to those NVIDIA GPUs. And this piece right here is what we're looking at replacing then with that FPGA and then the OpenBMC stack. What a BMC does, it talks up to the host, in this case, it's over LPC, to do things like initialize the system. And it also talks over FSI up to the processors in order to collect debug information. And there's something else they call an on-chip controller, which is kind of my baby. And it's the entity that does the power and thermal management on the nodes. And the BMC talks to that on-chip controller back and forth to collect sensor information, as well as do controls like, hey, you need to enter a different power mode. We need to save more power. I want you to boost performance, or whatever the communication might be. So that's just an overview of what the AC922 looks like, along with the specifics of that BMC. This is a different picture that I drew. This is much simpler, but it shows it, and it's an easier way to look at what was actually done. So we had a card right here inside that AC922 that we called the box elder card, and hit add on it that ASPEED AST 2500. So that's the main processing unit. It ran OpenBMC code stack, and then had the other RAM and flash and other things associated. Then we had a Molex 240 pin connector. So not the DC-SCM connector, because we designed this AC922 long before that standard had been in place. So we did our own connector and have all the interfaces like FSI, I2C, and GPOs to do the controls of the power supplies and the fans and everything that's on on that main planar. So that's the concept in most computer systems. Lenovo, Dell, whatever, would have this similar concept. They've got a BMC. They've separated out these various controls into these 2 control planes, but it isn't standardized. It wasn't standardized until DC-SCM. Our first step was to prove that we could boot it, and not even full function, but just, will this even work at all? So we took a FPGA, this RTX A7 FPGA, ran some code. We didn't run full OpenBMC. Yeah, that was not the first step, but we had some scripts running, and we were able to plug it into the planar, and we showed that at least it would boot the system. That not full function again. It wasn't doing full sensor reads, and it didn't collect errors and all the things that a BMC needs to do. But we showed that it booted it. And here's how we did that. This is the box elder card that we were just looking at in block diagram form. So this is the original one with the ASPEED chip on it, and there's that 240 pin connector. Here's the breadboard that we made. My colleagues from IBM in Australia wired this thing up. That's the FPGA board right there. So that's running those scripts, and then that just replaces that board that I just showed you, right? So it was this board. We replaced it with our own little homegrown thing, and then we were able to plug it into the system. And in fact, it did boot the system. And then, but again, not full function. So we need to take the next step. This happened about, maybe a year ago. Yeah, so now I'm going to talk a little bit about what is DC-SCM. So it's an open compute project, OCP sub work group. And what we're trying to do in this work group is define the form factor for this card, not necessarily the components on it. You don't have to have a certain processor or a certain root of trust. If you know what that is, that's a big deal now in the security world. But it does, but we're trying to define the DC-SCI. So first of all, it stands for Data Center Security and Control Module. So this is the Data Center Security and Control Module interface here, which is between that HPM board that you're planning with your processors and your power supplies on it, between that and your DC-SCM card. And you can see many signals, right? What does it say? Yeah, like 168 signals maybe. Yeah, 168 pin connector was in the 1.0 version. And this has to work for all the vendors, right? That's the trick. IBM uses FSI. That's our connection. It's an open standard, but that's our connection up to the processor, like I showed you on that first page. But other Intel uses PECI, right? Everybody uses a variety of different interfaces. So this has to be a superset of what everybody needs in order for it to work, in order for you to be able to do any planar out there, whether it's based on ARM, Intel, AMD, or IBM Power. So we got together and defined that interface. So another view of it, I wanted to show this. It shows that's a CPLD, right? Yeah, that's your serializer. So one thing we can do, because there's so many different GPIOs you would have to define, that we put a serializer in the middle. So you would take a standard GPIO that doesn't have a lot of timing critical issues. If it can stand a little latency, you run it through a serializer and you deserialize on the other side. That's an important part of the standard. And in the 2.0 standard, we enhanced that with something called LTPI, which is an LVDS transfer protocol interface. You can think of it as the same thing. It just does it a little bit differently, and it does it in real time, which is an important aspect. Now you also see down here the root of trust. That's what I'm talking about with this security. Everybody is going to be putting their own root of trust on here. In fact, if you're watching OCP, they announced Calyptra, which is a little piece of IP that is a root of trust that gets sprinkled out throughout your server, and then Hydra. So Hydra was the announced that it takes a BMC and this root of trust and puts it together, and it's all in the open. So people are potentially going to start adopting those standards in order to increase their security. So what the root of trust does, it's the first thing that boots up in your server, and then it checks everything else. So it checks the code load of your BMC. Is that correct? And then if anything else needs to be checked, it goes through that root of trust, and you've got the signatures with the keys. So if you're in the security world at all, you'll understand kind of what that does. So people are going to want this. They're going to put their own root of trust on this card. And the point of LibreBMC is, yeah, in fact, not only is it a root of trust and a BMC ASIC, but these can be FPGAs, which means it's another step. We're reducing another level of the attack vector, because that's not an ASIC and that's not an ASIC. So you can inspect what's going on inside of all of that hardware. All right, so the next step here in the process is to support this DC-SCM standard. We took a Antmicro company, and they built a card for us, which has that FPGA on it. It's this card right here, actually. I have a picture of this, I think, later on too. But so they built this card, and again with the FPGA, and then we needed an interposer, because we had that on our AC922. We had that 240-pin Molex connector, so we have this built. It's an interposer, so you plug the DC-SCM card into that, and then that plugs down into that chassis I showed you, and you connect it into your system. So that was next step. Have that built. We did that, and that's been we've had that for a while. There's pictures of them for those of you that aren't here to see it live. Again, this is the DC-SCM card. It plugs into that interposer. The scale doesn't look like it would fit here due to the scaling, but it does. We plug that into that AC922. I showed you that we had that breadboard in there. We had the original card. Now this is the DC-SCM card plugged in. That's in that interposer and installed in the AC922. And just recently, we got this actually working. A company called Code Construct out of Australia. They picked up the mission to get it all working. So now it is, in fact, running. It's running the Linux kernel on Microwatt. It's doing full function OpenBMC. There are still some improvements that can be made. For instance, we're still bit banging things like ITC and FSI. So there's not actual gateware to do an FSI implementation, but there is. So we're bit banging. So there are improvements that can be made. But it does fully boot, and there's instructions here. If you follow this link on how you can replicate this yourself. There are some hardware problems with the interposer and the DC-SCM card, so you're going to have to make a few hardware changes if you want to replicate it. But it is definitely possible, and the instructions are out there. And then there is a demo that I'm going to show you on it booting. Just to just approve it. Let me see what the next page is. All right. I think I'll do the demo, show you that now, and then we'll talk about next steps. So how do I make this thing? How do I get out of this and make it go to this demo? Doesn't seem to be live. Squirrely. I don't have any. Oh, there it was. I'm gonna start it over here.
This portfolio and keep your ears upon the networking best for working performance. This is implemented live data. This is for the crazy one. We don't need to modify function. You have to lay in the BBC. Just the place that online. What there is one. Just back the. It's kind of what we have. So we can do that. Stay on the code. Yeah, a few events for reason clear. Well, there's that's generally. We also have access to the radio. Probably we can get set up. We do have an nation set up. Using the animation can be set to the event. You say that 20 years set in the green line. It's a third issue. That's important to know. Full time over that. So So we've got the power. Yes. The BMC, the host patterns, stuff, slides, and then continue with the start. We do get to more than one. So there's you get the first time. At the end of the hour, the BMC got the or step on that person. And the rest of the
We can cut this. All right. Maybe that wasn't as thrilling as I thought it was going to be.
We encourage everybody to see the video and
Yeah. So let's go on to, there are a couple important pages here to get to. Get rid of this. Anyway, the video just shows, yeah, in fact, you can boot a system with an FPGA, which, and even Jeremy, who did that video when he first took on the project, didn't think it was going to work. So I thought it was interesting to at least see it. So what's next? This is an important, really important slide, I think, because there's a lot of activity going on in this realm. So we just proved it. You can boot it with an FPGA. We can support this DC-SCM standard. There was a lot of talk about DC-SCM 2.0 at OCP. And so what are we going to do as a work group going forward? And it's exciting for me to see the various ideas here that we can do. So one thing is we could potentially reduce the number of components on that board. This board right here is a lot of empty space. We could sweep things together, make it a smaller form factor. We could get this connector smaller by using more serialization to get broader adoption of the card itself. And there's talk in the work group of potentially doing that. We could, on the FPGA side of it, as he talked about, we could add more gateware in order to increase the speed and make it a better, really a better platform. We can support more FPGAs. That was an Arctic A7, but there are other potentially better options like a Lattice ECP5, and we could migrate this project over to support those. Would love to support other system types. So not, have this card not just plug into an AC922, but plug into an ARM-based system or an x86-based system to get it even broader adoption. We could have a new core. I talked about microwatt. That's the core that was running on the FPGA. There's a new one that the Power Foundation has supported, and that we could replace the core with that. what are some interesting ones? So interesting, I think, down here, when you talk about redundancy and this one-to-N support. There's a lot of talk in the industry about this future of computing, this cluster computing, where you would have maybe one of these cards in a chassis, and you would have multiple planers from different vendors, and then you could have all your memory sitting somewhere else attached via CXL, and you would be able to compose this system then by, so as a job would come in, you would create the system that you needed dynamically using whatever cores that would run the best on and however much memory. And in order to do that, which I think is probably the future, you're gonna need some help here with the standard. We're gonna have some further security enhancements, but I think there's a lot of exciting things going on in this space. I encourage you to join, which leads to the most important slide. Just to join us on this action. I'm running a meeting on 11:30, and that's you can go to this link and see the actual time, the time and the day. But that's where we're going to talk about the future. We've hit this milestone, we proved it. The next thing is to start deciding what do we want to do going forward in the future, and having a large community involved is a real big help and a lot of fun. And by the way, you can buy your own AC 922, just pointing that out, $5,000 if you want with that supercomputer. You don't get the GPUs, but to have something to play around with, that's a pretty cool option. So you can follow these links, and I'm out of time, but thank you for your time and attention. And that's it.